Yes. Okay. Hi, everybody. Welcome to the final IARC Salon of the 2020-2021 school year. It's been a wild time. I think next year we'll be going back to hopefully to in-person IARC salons, and that'll be nice, cookies and tea. For today, I just want to make sure that everybody knows how to operate Zoom. If you all could just make sure that you are muted throughout the duration of the presentations, and also if you have questions, please put them in the chat. I think the format, and Cease can confirm this to me, is unlike what we've done in the past. We have these three presentations, and we're going to actually welcome questions after each presentation rather than all at the end. So please do be prepared with questions, and you will be able to unmute in the event that you want to ask your question out loud. And aside from that, to save bandwidth, perhaps, while people are speaking, you can turn off your cameras, and that is, I think that is it. Cecilia, was there anything I missed?
That should be good. So thank you all again for coming. So we are doing, to celebrate the end of the semester, we thought it would be a great idea to highlight some of the research that our graduate students are doing. And as luck would have it, the students who volunteered to do this and had the availability to do this are all atmospheric science students. So we are going to get a preview of some of the research coming out of the atmospheric science department, and it is all a little bit different. It's all not just about the atmosphere, which is pretty awesome. Our speakers today are James White, Hannah Brink, and Amy Hendricks. And if you guys would like to do a brief bio when it's your turn to speak, feel free. And I think we'll go ahead and let James take it away. Oh, and sorry, yes, we are doing things a little bit differently this time because the topics are all, the research topics are all a little bit different. We thought it might reduce some of the clutter if we opened questions after each presenter. So we'll welcome questions at the end for everyone, again, if you didn't get a chance to ask one, or if you've thought of one during another presentation. So that's something just a little bit different. And with that, we'll go ahead and let James start.
All right, gotcha. I'll go ahead and share my screen. All right. Everybody can see that, right? All right.
Yes.
Cool. So hello, everyone. I'm James White. I'm a master's student here at the here in the Atmospheric Science Department, and I work with the Alaska Center for Climate Assessment and Policy. My advisor is John Walsh. I am graduating this semester, so imminently. Thesis submitted and everything, so that's exciting. And I've also just started a job at the National Weather Service in Eureka, California. So I've been working there for about a month, though I'm still in Alaska for a few more weeks. So anyway, and I'm here to talk about what my thesis research was, which is applying machine learning to characterize and predict wildfire activity in Alaska. This is just my AGU presentation from last year, repurposed, so I'll probably speed through a few of the slides to save time. And if you've already seen that presentation, sorry, but this is basically that again. So first of all, I just want to go over some background of what wildfire is in the state of Alaska, because it's a big deal, as I'm sure I don't have to tell anybody that lives here, is that fire is a big deal. And it's always really good to get a sense of scale of just how much of the interior has burned in the past 70 to 80 years or so. That's basically what this map here shows. It shows how fire dependent the ecosystems really are here. So it's a huge part of the ecosystem, and it can be very difficult to predict because it's highly variable from year to year. And it's also something that's highly influenced by climate change at the moment. So, so understanding how fire behaves and how it grows is a really important issue. Oh, sorry if my cat is meowing. So when it comes to predicting fire in the state, there's a lot of different metrics that are used by fire managers and weather forecasters to try and understand and predict fire growth. One of the most common systems is called the CFFDRS, which is the Canadian Forest Fire Danger Rating System. And that's a very qualitative system. Although it has numbers and metrics associated with it, it's kind of based on user experience. At the same time, there are these kind of complicated physical models that are run on computers and supercomputers to estimate fire spread over given geographic areas. But those are usually only accurate to a few days in advance, and they require a highly skilled and trained personnel to run and interpret. So there's a need for this kind of easy to run qualitative prediction that can be used over longer time periods. We have these indices, which are used over weeks to get an idea, and we have these complicated models over short time periods, but there's a gap there in the middle that can be filled. So that's what we decided to do here, see if we can apply machine learning in a very simple way to try and address that gap. So going over a little bit of the methods here of my thesis. The first thing you need to do if you want to predict wildfire spread is you need to have some measure of wildfire activity. There's a lot of different ways you could do this, but the simplest method here is to use satellite detections from MODIS, a satellite sensor called MODIS. Has been in operation for about 20 years now, and it's able to give us daily counts of fire in the state. So what we did is we took those detections from MODIS, we paired polygons at the end of every season, fire-burned polygons from the Alaska Interagency Coordination Center, and we paired those MODIS counts with the polygons to get a measure of daily wildfire activity on fires around the state during the summer. And that's an image of what you see on the right, is you'll see what some fire polygons look like and some of the MODIS counts that might appear in some of them. In addition to that, we had to say, okay, we have our fire measure. What are the things that could predict wildfire activity on any given day? So we included a whole bunch of different things, mostly weather variables, because those are the most fastest changing part of the scheme. So if we're looking at daily, weather variables are probably the main control of daily changes. And we included several different sources, including gridded reanalysis, which is a kind of weather model output, as well as station data to see what in situ observations get to show us. We also included things like broad vegetation type, which we measure with spruce fraction, and a few different things. What this results in is a very large amount of data that we can train a machine learning model on. That is 26,170 entries in the database. So those are fire days. So any day that a fire was active in that time period gets counted in there. And then to better interpret this data, we then subsetted this data into their sources, which will make a little bit more sense when I show you the results. And the last part of the methods here is the machine learning model we wanted to apply. So for those who aren't familiar with machine learning model, at its very basic level, a machine learning model is any kind of computer algorithm that is able to improve its own performance based on past results, i.e. it's learning. That's why it's called machine learning. So in this case, we used a machine learning algorithm that's called a random forest model, which is based on something called a decision tree. Decision tree is basically how the model will try and create these branches in a data set to better classify or in this case, make a numerical prediction to create something. A random forest is a special type of decision tree that is made up of an ensemble of several different decision trees working together that helps to reduce a problem called overfitting, helps increase model confidence, basically. So taking a look at the results, what do you get when you do this? What variables are important? What does the model rely on? How well can we forecast daily fire activity using this? Well, let's take a look. So the first thing we want to know, okay, of this like 30 or so variables we threw at the model, what is it actually using? What's actually important for wildfire prediction? So what I have here are several different data sets. We have station-based data sets up here in the top several. We have ERA5, that kind of model-based stuff in the bottom. And these include several different subsets of things, such as the weather variables we thought to include, the CFFDRS, those index variables based on different sources. We have some climate variables in there. And at the top here, we have this baseline. Baseline is just using the previous day's fire activity, because that's the single most important variable, as we tell the model what was the fire activity the day before to predict tomorrow's fire activity. So we can kind of scale the fire based on that. Is we want to see improvement above this baseline metric. And what we see here is that we can do better than that, which is good. We can see we have an R squared, so coefficient of determination in some of these of around 0.55 to 0.6, which is pretty good for a problem as complex as this. And some broad takeaways here is the ERA5 derived data is better than the station derived data. And using things like the CFF-DRS adds value when you have station variables, but it does not add value when you have model data. So operationally, we use those indices. Well, it makes sense. The use of station data supports that, but maybe not necessarily if you're using past-looking ERA5 data. Drilling a little bit further, we determined, okay, those forecast variables are really the important part. That's actually what we want to use. But what in that subset is important? What we could see is when we do a single variable removal, we see that the previous day activity is by far the single most important part, but nothing else was much more important beyond that. So we did some two variable models. And when you have two variable models, what we can see is the most important variables that pop out are still the previous day fire activity, but also now we have like maximum vapor pressure deficit for the day, total precipitation, average cloud cover. So we get to see some other variables that are important in there. And these are largely in line with past research. Finally, I want to wrap you up by showing you what does this data actually look like if you want to look at it in the field. And what you can do is you can create predictions for fires that look like this, where you have a machine learning prediction in orange, we have our observed data in blue, we have our baseline data in green. So this is a pretty good fire, the rock fire, which was a very large fire in 2015, I believe, if I remember correctly. We can see, just given our model as is, we can predict it pretty well. Impressive. However, this prediction, we always know what happened the day before. So let's remove that variable and make the model predict that on its own. And the reason we do this is because this is what a meteorologist would have to do. If you're making a multi-day prediction, this is exactly what the model has to do. So when we do that, we see we lose some model skill. This peak is suddenly higher, this peak isn't quite as good, but the overall timing of things, even throughout this 50-day period, is pretty well maintained. So that means there's not much error propagation in the model. So this is a very useful metric. And there's some different reasons that could cause this. And lastly, the last thing we wanted to do was apply weather model data. So actual forecasting data, what would a forecaster see if they did this? Because right now we're using ERA5 data, which is essentially a perfect weather forecast. But if we used actual weather model data that a forecaster would have had access to at the time, well, we can see what this model could have shown us 2 weeks or so in advance. And that's what we see here. We see these different members of an ensemble weather model making 2-week predictions as we move through this fire. What would this model have predicted in real time? And we can see this early part of the fire is pretty well predicted. It's getting these peaks pretty good. Magnitude isn't always great, but the timing's pretty good. This peak here isn't well forecast at all. So sometimes the model messes up. It doesn't have all the information. Neither does the weather model. So there is real challenges and improvement to be made in this kind of result. So to pull it all together, there's real potential for machine learning and wildfire prediction. It's a really cool field. There's a lot of research going into it right now. So it's a lot of great stuff that can be done there. But a model like this is going to struggle to get the magnitude, even if it gets the timing of things. But it has real advantages in that it can be automated. It's quick, it's easy to use, but it can only be used for what the data it's trained on. It doesn't have a geographic component. So there's also a lot of things it needs to improve to really be operationally applied. Sorry to take up a little bit too much time, but there you go. So if you have any questions, you can let me know.
Yes, so like I said, we are doing things just a little bit differently. We are going to take a few minutes for questions for James's presentation. If you have one, please feel free to unmute yourself and go ahead and ask it. You can also type it into the chat and I can read it out loud as well, if you prefer. James, one of the questions I've had, because for the past 2 years, I've seen you work on this research, but has machine learning been used to predict any other weather phenomena or things like this?
Yeah, for sure. So machine learning is very broad, and it's definitely a hot topic, hot button issue of research. So it has been used a lot in meteorology. Just for example, I mean, if you want a very weather service example, there's a system called the National Blended Models, which is kind of the state of the art weather modeling, what things are going to. You take things like the GFS or the NAM or the Euro model or whatever, all these different sources of models, and you blend them together. And some of that blending is done using machine learning algorithms that weight different models under different circumstances. So that's just one example. Machine learning can be used in more research applications, like in climate, to identify climate patterns, identify things like radar signatures for image recognition, all sorts of things. So yeah, it's a very broad field of research with a lot of application.
Hey, this is Hayo. Thanks, James. I've got a question for you along those lines. So as I understand it, you know, the blending and the expert knowledge of forecasters with the weather service or other forecasting services is really a key element of the forecast. In terms of fire weather forecasting, the work that you're doing, how important is that type of knowledge? And do you see the machine learning being something that can be blended with personal expertise readily?
For sure. So fire forecasting is, I feel like in some ways a little bit back where general forecasting was a while ago, in the sense that a lot of it is still kind of intuition experience based, because the questions are so much more complex, of like you have these local terrain issues and all sorts of stuff going on. And so that kind of intuition is really important. That's where a lot of these fire indices are used. You know, while they're based on these numerical objective things, their interpretation and use can be very subjective and intuitive. And that's just how it's worked best. I think there definitely is room for machine learning to come in and aid these things. I think what's important to remember in a lot of these conversations, you kind of get into these narratives of like, oh, the machine learning is going to come in and replace people. And that's not really the case. All it really does is it gives forecasters more tools to do their job. And it can provide some clarity or information or context where things, you know, might not have been there before. So I guess that's what I envision it is. Yeah, you can definitely integrate these things to provide further clarity and give forecasters the ability to communicate the information they need to. So yeah, I don't know if that answered your question, but
No, that's great. Thanks.
All right, any final questions for James before we move on to the next speaker? Okay, then. If you do have a question for James later, feel free to type it into the chat box and we can address it at the end. If not, we will go ahead and move on to Hannah.
Hi, my name is Hannah Brink. I'm graduating this semester after defending my master's thesis under Nicole Mulders, and I did my, well, I guess it's time to pull up my slides to share my research. Screen. Can everyone see that?
Yes, we see it.
Okay. As soon as it loads, yes. Okay, so basically I did my research on a comparative case study of gravity and mountain wave phenomena in Fairbanks, Alaska, specifically how they impact weather, and I'm giving you the short version, basically. So first I should explain what exactly are mountain and gravity waves. Well, gravity waves are the result of the balance between gravity and buoyancy forces, as you can see in the free body diagram here, and you can see other effects, other things they may be affected by, but generally we can take it as buoyancy versus gravity. These happen in response to vertical perturbations in the atmosphere from external forcing, or from instabilities in otherwise stably stratified atmospheres. And it's going to be important. Stably stratified atmospheres are when air particles are in equilibrium over same pressure surfaces, isobaric surfaces. mountain waves are basically a subtype of gravity waves, and that they're caused by external forcing, but that external forcing is irregular terrain and thus air flowing over her mountains. And you can see how they form in the diagram below, and how they may result in lenticular clouds due to the lifting of warm, moist air due to this perturbation of mountain waves. Lenticular clouds are basically smooth altocumulus clouds affected by high wind speeds. You may think of them as UFO clouds. So there are several local impacts that generally include an increase in temperature and basically warmer, drier air on the leeward side, as well as higher wind conditions. And basically and these also can create instabilities on that side, which is a hazard for generally air travel. And there are several documented cases of aircraft accidents as a result of mountain wave influence in the area that was not properly accounted for. But they may also cause other travel effects, which I'll discuss. They can also affect the upper atmosphere if gravity waves propagate vertically, and this is more pronounced if gravity waves trapped between air parcel layers, and then gravity wave breaks, such as like when you think of water breaking, it's generally the same sort of thing. This only happens when the buoyancy and winds are sufficiently high. And if this energy propagates into the stratosphere, it can affect upper atmospheric circulation and could create high pressure systems that can create sudden stratospheric warmings. And basically what these do is they can push down the upper atmosphere circulation or the polar vortex down to the lower latitudes. And these can create inclement weather events that you may hear about in the lower atmosphere. It's not the sole cause of sudden stratospheric warmings, but it is a possible instigator. So what I did in my study is I basically took radiosonde data to acquire vertical profiles to examine weather parameters specifically in Fairbanks. This limits horizontal data, but part of my motivation was to get as much information as I could about mountain waves without using horizontal data as is recommended. You'll see. So I calculated gravity wave energies and examined effective atmospheric parameters in order to see the resulting weather phenomena from gravity wave events. Keep in mind, I have a parameter for a vertical wind speed, but it's calculated very broadly as just change in geopotential height or pressure over 12 hours and shouldn't be taken as instantaneous data, but it will be important to make a point about pressure that I'll go over later. So I have two cases in 2016 and 2017, both in December. So about the same season and generally the time of strong inversions. So both these involved a jet stream over the Fairbanks area because that was because when I was looking for cases that was looking for buoyancy effects was commonly connected with the jet stream presence over Fairbanks. You can see in the map here that you can have mountain wave effects from the North Burke Range, South Alaska Range, or technically the East Yukon, but since the upper atmosphere circulation flows from west to east, I didn't really expect that. So, but the 2016 event came from the west where there's no significant mountain influence, so it's taken as a gravity wave event. 2017 case is when you have the jet stream over the Alaska Range into Fairbanks, and that will, so this is a way to compare a gravity wave event and a mountain wave event. And this will be over multiple days, but there are specific dates that to watch out for on each event. The 24th for this 2016 case and the 8th of 2017. So here's some data for the 2016 case, not all of it. This is reduced. These are basically pressure height plots that indicate the measure of what the data is over the heights and over time. Time is on the x-axis. And you can have the anomalies too, in which case the anomalies are the data subtracted from the climatology to see what's actually different. And everything is smoothed over one day in order to remove diurnal forces. Like basically day and night cycle is not a factor here. So you can see after the 24th, which is around in the middle of the plots, you can see a positive change in temperature and dew point temperature and some relative humidity, but you have some dry air towards the surface. And then you also see a negative change in geopotential height, which is indicative of a positive pressure area being formed. You can see them here. You can also see the increase in wind speed, and the wind speed you can see the jet stream influence as indicated by jet stream wind speed of over 30 meters per second. That's the threshold. And everything generally happens after that jet stream effect. And so of importance is a positive climate mean anomalies, but also the surface pressure are high after the event. Do I need to slow down? Okay. And then here are the wave parameters. The Brunt-Feisal frequency is basically the buoyancy frequency, and the Richardson gradient number is a ratio of the buoyancy frequency versus the wind shear. And basically, the lower it is, the more unstable it is. Basically, the threshold is about 0.25. And you can see, after the event, or after the 24th, you can see unstable atmosphere around the atmospheric boundary layer at 800 hectopascals, which is basically the border when Earth's friction stops having an effect. And you can see that how it can relate to the buoyancy frequency. And then there's a score parameter, which is basically a measure of the vertical propagation in the atmosphere by measuring the buoyancy frequency and scaling it with the mean horizontal wind speed. If it's constant with height, it's more likely to propagate. But if it's suddenly negative, as it is in these two areas, then you have a higher chance of trapped waves and thus perhaps gravity wave breaking later. So you can see that there's wave effects going on here. And then there's also the gravity wave energies, the potential energy, which obviously something was going on before the event, but perhaps was scaled out after the event. And then the kinetic energy is largely influenced by the jet stream. The kinetic energy is generally higher than the potential energy. That's just normal. Okay, so here are some Skew-T diagrams that I created, and I put it in GIF form. I hope it's not too fast. These are generally used to measure change of temperature and dew point temperature with height, right, and can be used to determine several weather phenomena. I'm just going to point out the inversions, which are indicated by suddenly higher temperatures at a certain point, and which is and higher temperature is to the right. So generally, if you see it going to the left in the troposphere, that's generally normal. There's a point, once it hits the stratosphere, it's going to increase, and at the atmospheric boundary layer, it may also increase with height. But so I'm waiting for the 24th here because that's the event date. You can see that there are inversions, but it's generally, I think that, okay, 24th. And you can see on the 12th, hopefully you can see some unstable event going on. Okay, so basically the 2016 case was a mild event. But here's a 2017 case where you have several propagating points, but the one in particular to point out is the 8th, a little to the right of the middle, where you can see positive changes in temperature and dew point temperature, relative humidity, and wind speeds in particular. But also you see again the high pressure system area towards the surface, right, basically on the event, just right after the jet stream stopped having influence. And this is something that we saw in the 2016 case as well. So you can see that all these are instigated by the mountain wave having effect around the 7th after the jet stream. And that's a higher wind speeds afterwards. And then here again is the gravity wave information. And here is a static instability due to the low Richardson gradient number and the corresponding with higher surface Brunt-Feisal frequency and higher score parameter. But you can also see okay, so when there are any changes in the vertical column of the atmosphere, which is basically that height, you generally see heat changes propagating over the entire column, but you don't see that here with some changes being highlighted. And then you see these other changes, such as increase in buoyancy and evidence of trapped waves. And if you look at the gravity wave energies, you can see the gravity wave potential energy happening roughly after the gravity wave event, after the jet stream event, as indicated by the kinetic energy. And these are about 10 times higher order of magnitude than just a gravity wave event. And here's the Skew-T plots again. You'll want to wait for the 8s in particular. Like there may be some things going on, but nothing too unusual. 12, the 8s, and then that's the point of instabilities, where you suddenly have strong inversions continuing for a while. Okay, so to conclude, we generally have strong static stability in Fairbanks winters with its high inversions, and they can be strongly linked to gravity waves, which makes Fairbanks a nice natural laboratory. I can only hypothesize because these are limited case findings, but that mountain waves are generally stronger than gravity waves. But these events indicated high temperatures with wet and windy conditions. And I didn't go over much, but in 2017, the surface temperature hit above freezing, which would create adverse road conditions, and the instabilities would also create adverse air travel. So what I found interesting was the localized high pressure systems on the surface after the event. So you can see it's real, but and these happen below the atmospheric boundary layer when Earth's friction takes effect, and most of the instabilities happen around that point, which would indicate a connection between the atmospheric boundary layer and some potential adverse systems. And I hypothesize that gravity waves can instigate strong surface high pressure systems. And these are generally important to look at travel conditions and basically possibly be a forecasting predictor for, basically if you can see the jet stream heading over Fairbanks, and that could be from the mountains in particular, then that could be an indicator for travel safety. That's all. Thank you.
Thank you, Hannah. So again, if you have any questions, please feel free to unmute yourself. I will say I like your comment that Fairbanks is a natural laboratory.
Yeah.
One of the questions I have, and I can't remember if you answered this in your defense when I was there, but you're looking at 2 winter events and what that means for the atmosphere in the winter. Did you look into any summer events and what that would mean for summer, since obviously winter and summer in Fairbanks are so different?
There's not as many in the summer, and there was another paper published here. I don't remember the author off the top of my head, but they looked at how many gravity wave instances happened, and most of them were over the winter and died out during the summer and then picked up again in the fall. And basically none were detected during the summer. There was one summer case that I was looking at and wanted to include, but I found that the case was not strong enough to warrant too much study. So basically, like in the summer, the atmospheric inversions and static stability is not so much creates conditions that are not so helpful for mountain wave formation.
I see, thank you. Any other questions? All right, so again, if you think of a question later, feel free to type it in the chat. Hayo says, thank you, great introduction to an interesting topic. And we'll go ahead and let Amy get ready for her portion.
Oh, I see. Hi there. Unmuted now. I'm gonna go ahead and share my screen. hope everybody can see that. So coming out of you from left field here, I am an atmospheric science PhD student under Uma Bhatt is my advisor. And yes, today I'll be talking to you a little different here, supporting coastal community resilience in Alaska, an evaluation of the CIS for Walrus Outlook. And so,
really quick, we see the abstract. Is that what?
No, sorry. Don't pay attention to that. Hold on. Oh, wait. Did I pick the wrong thing to share? Can you
There
see?
we go.
Okay, there we go. Okay, great. So here's my title slide. So I guess a bit about my background, like how did an atmospheric scientist get into an evaluation of co-produced actionable science project? And my background is really heavily in atmospheric science and meteorology. And my master's thesis focused on climate-driven vegetation biome simulations. So it was a paleoclimate paper project and also looking at future climate projections. And starting my PhD here, the project was focused on climate drivers of vegetation change in Southwest Alaska. And through this project, I was that project, the Yukon-Kuskokwim Delta project, I was really fortunate to be able to travel down to Bethel and attend a couple of steering committee meetings with the Chilista elders, a group of Yupik elders in the region. And my research focused on the climate aspect of the study. And one thing that became very apparent when we talked about climate and climate change and environmental change was how tied that was to a subsistence lifestyle. And so here is where I really started to gain an appreciation and interest in the impacts of climate and climate change and variability on food subsistence security. And so this project came up at the perfect time. I was wrapping up the other project, and this one really hit on all of my interests. And I am excited. All of this is new for me, so I am definitely a new learner here. I started this project in August. And let's see, what did I want to say about this? Anyway, co-production of actionable science. Let's just go ahead and get into it. And on this title slide, you can see all of these different logos. And I think this just kind of exemplifies how many different groups and how many different people are involved. Like, this isn't even everybody that's affiliated with the project or all the groups that are affiliated with the SIWO, the CIS for Walrus Outlook. I'm just going to call it the SIWO from now on. And shout out to the PI on the project, Dr. Nathan Kettle. He has been really great guiding me through this. Let's see. So to get started, what is the SIWO? It is a resource for Alaska Native walrus hunters and others interested in sea ice and walrus in the Bering Strait region. And so here I have a map of the region, and there are 7 communities that are of focus in this project, and that's Shishmaref, Diomede, Wales, Port Clarence, Nome, Gamble, and Sabunga. And so what is the SIWO to even begin with? It is a weekly outlook. It comes out during the spring, so typically March through May, when the sea ice is moving through the region and the walrus are riding that. And what does it include? It includes the National Weather Service weather and sea ice forecasts for the communities in the region. It has local community observations that are sent in with sea ice observations, marine mammal observations, and pictures. And then there's also opportunistic sources of information, and I'll show you what those look like. And this came out a decade ago. It was a pilot project for the International Polar Year, which was 2007 through 2009, I believe. And just shameless plug, week number 5 Outlook is coming out tomorrow at noon. And I'm always really excited to read these. I learn a lot about sea ice in the area. And so, this project really exemplifies, or the SciWo really exemplifies co-production of actionable science for decision-making. And this project was designed and created for walrus hunters who need that extra source of information in a time of increasingly variable environmental conditions that they have to navigate. And so it's about safety, it's about food subsistence security. And, I keep bringing up this co-production, and this project wouldn't be, it wouldn't function without the knowledge and expertise of all of the groups that are involved. So this figure here is from the proposal for the project, and that top half above the line there is everybody involved in creating that weekly outlook during the SciWo season. And that's the local observers from the 7 communities that I listed, the National Weather Service, and other opportunistic sources of information that can be added. And all of this comes to ARCIS, and the project manager compiles all of this information and presents it in this nice package. And throughout the year, there are opportunities for this advisory team, and there are a couple of people I see in the participants here that are, Hioiken for one, involved in the SciWo much more intimately. But there's this annual guidance from walrus experts, sea ice experts, observation network experts, just really incredible people with vast wealth of knowledge. So what does the outlook look like? This is just a couple of screen caps that I got from the ARCIS page. You can also access it from the Facebook SciWo page, which is, I guess it sounds like that is the way to access the SciWo. It seems to be preferred. But on the left, we have sea ice forecasts and sea ice concentration forecasts. The next image is the remote sensing images. Those are satellite images with all of the towns listed, or the villages listed. Getting in as close as we can to the region. Obviously, one of the limitations is going to be things like resolution. Then on the far right upper part, we have observations. So all of these came from last week's outlook. Don't have tomorrow's yet, but over on the right, we have observations from Diomede, and that's going to be talking about, here Marty's talking about snow and whiteout conditions and where the ice edge is, and then they send in these pictures. And at the bottom on the right here is an image from Rick Toman. He's pretty active in sending in these annotated satellite images. And I'll be totally honest, I learn a lot from his images. Looking at this initially, I wouldn't be able to tell what's a cloud, what's ice, but these annotated images are fantastic. So it's been around, the SciWo has been around for a decade. We're going into the 11th year here. And what's working right and what's working well and what's not, what can be changed, what can be addressed, what recommendations can be made. So the project manager and the steering committee for this evaluation project came up with a list of questions that they're really curious about and looking for ways to improve the SciWo. And things that came up are what platforms are most effective in disseminating the SciWo. It really sounds like Facebook is the preferred platform there. What barriers impede information access and use? And one of the biggest ones are your internet bandwidth when you're out in the Bering Strait region can be atrocious and incredibly expensive. What stakeholder groups use the SciWo? So we know that the intended users are accessing it and participating, but are there other users who are accessing the SciWo for various purposes? But asking the question, what's the most helpful? What's the most useful? What's the least useful? maybe the discussion on sea ice isn't that useful. I like to think that's not the case, but you know, learning what works and what doesn't, and can anything be added that would help make the decision to go walrus hunting or help navigate that sea ice. And then another question is, how valuable are the outlooks for facilitating information exchange? And that's not just among communities, but among also the advisory team, and also the National Weather Service is something that they're curious about. So what is an evaluation? An evaluation is a way to look at this project and think about things that would make it successful. And this image, or this slide here, the SIWO evaluation framework, is really my thought experiment. And it's, you know, constantly in flux with the new information and new sources that I can take in. But there are 4 particular sources that have gone into this thought experiment. And when we ask these questions of each different group, we'll be evaluating them in the context of these indicators. And something that I learned through my literature review and my interpretation of the literature is that there were these 5 major elements that go into co-production. And those are the knowledge systems, like who's coming into the project, what does that process look like? Is it collaborative? Is it back and forth? Is it real co-production? And looking at outcomes, you know, not just the SIWO weekly product, but what else comes out of it? How else is the SIWO getting out there? What are people's reflections on things? There's equity, and this one's kind of a, you know, this one came out of a co-production wheel out of COERIC, I believe. I cited it here, Behe et al. 2020. But that was co-production co-production framework from an Alaska Native perspective. And that was an invaluable resource as well, because you know, we're evaluating a project that has 2 totally different separate knowledge systems, and thinking about what are the values and what's important to the intended users, who are the Alaska Native walrus hunters. And equity is huge. And so this is things like equity to access, equity to participate and give your feedback. Let's see, then the other element there is a communication, like how much back and forth is there? Is it understandable? Things like that. So this, again, is just kind of my thought experiment to put in context with other literature and other evaluation work that's happening, looking at actionable science, co-production of actionable science, and then on top of that, you know, that extra element of co-production of actionable science for Alaska Native subsistence hunters. Let's see. So kind of just, you know, I'm in the midst of this. I don't have any finalized conclusions to share with everybody. I've only had my 1 interview so far, and that was with the project manager for the SIWO. And so right now, based on responses from this person, we have been able to develop more protocols, more questions, and we're hoping to submit these to the review board coming up soon. But I failed to mention here that even this evaluation project has an element of co-production in it, in that we're constantly going back, trying to go back to the steering committee for the evaluation and getting their input and asking, are we hitting the questions that you want answers to? Is this getting at what would make a good recommendation for the SIWO? Things of that nature. So after that, we'll interview select folks, and that's going to be like about 20 people, including the local observers who send in their observations and who are also the walrus hunters. We have the advisory team and a couple folks out of the Weather Service, as well as other coordinators for the SIWO. And after we go through this process of interviewing and hearing what everybody has to say, we want to get a broader understanding and kind of just broader view of how people feel about it, who uses it, how useful is it. So we'll create a questionnaire, and that's going to go on Facebook. I think it'll also be emailed out to groups. But again, Facebook kind of seems to be the way that people access the SIWO. And then, coming down to analyzing the transcripts and the questionnaire results and trying to figure out what were the themes, what were people's likes and dislikes, and can we make recommendations to ARCIS with that information. And so far my experience is showing that ARCIS and the project manager and everybody involved in the SIWO is just anticipating, like so excitedly waiting to be able to make changes to improve the SIWO. So, after we make our recommendations, I'll be waiting very expectantly to see what the response is, because everybody involved really just wants to see this be the best product that it can be. So I am excited for that last step there to see what comes out of that. And with that, it's kind of my little overview. If anybody has any questions for me, I'll go ahead and take those. I will also point out that Hayo and Olivia Lee, who are also participating here, are far more intimately involved with the SIWO, and perhaps they might be able to answer some questions if people are interested in the SIWO itself.
Thank you, Amy. So yes, any questions, feel free to type in the chat or unmute yourself and ask.
Hi, Amy. Thank you. That was a super neat overview, and I didn't know you were working on this project, and what a cool direction to be heading in. I love it. I don't know much about the SIWO project at all, so I was just learning all about it as you were describing it. Could you say a little bit more about the local observers and like specifically what kind of observations they're making, and then how they report those to the SIWO community?
Sure, yeah. So one thing I was excited to hear amongst the many things that I was excited to learn about was the relationships that were already established by the people that take these observations. So relationships had been established with the local observers. How am I trying to say this? And so that was a good foundation to have consistent observations being sent in. And observations can be things like, where is the ice in relation to the community? How is it moving? Is it fast? Is it slow? Is it bad ice? Is it good ice? Are they seeing walrus or other marine mammals like seals on the ice? Things like that. So that is a question that I have for the local observers when I am able to interview them, is what are they looking at? What makes them think to observe these things? Why are they important? And kind of what goes into their decision-making process to go out walrus hunting. Does that answer your question?
Yeah, it answers a lot of it. And then how do they get the observations to the community? Like, what are the reporting mechanisms?
So observations can go two different ways. And again, this is based on the pre-existing relationship. So some observations go to Lisa Sheffield Guy at ARCIS, and she will take those any way she can get them. Some people text them to her, some people email her, some people like Facebook message her. And then other observations go to Olivia Lee, who's here, and she has an observation network that I will be asking her a lot of questions about coming up.
Thank you.
Yeah, thanks. Good to see ya.
All right, any other questions for Amy or any of the other panelists we had today?
guess I have a question, Amy. It doesn't sound like this is really relevant, but just something I've been thinking about. A lot of organizations like the SIWO have a lot of or tend to have a lot of turnover. People that are very knowledgeable leave or get disconnected from the organization or something like that. And then, sometimes the organizations like this can get kind of lost without that individualized knowledge. I'm just kind of curious if there's if in SIWO or even just other examples, if there's good examples of resiliency against that issue.
That is a very important indicator that came up in a lot of the literature, was the turnover. And that goes back to the importance of relationships. And so that is something that I've found that has not happened a whole lot with the SIWO, was turnover. And people who have been involved from day one, and people who weren't there for day one have been involved for many years, and their involvement goes back to pre-existing relationships with the project manager, or their connections with observation networks or community observers. So turnover is an issue when it comes to co-produced. Oh yeah, Olivia Lee here has a great point. Most turnover happens when the elders have passed away and we work with younger hunters. So there is an aspect of that as well. And hoping that that knowledge will get passed on so that they can continue to help with observations. But that's a good point. Yeah, turnover is problematic, or can be.
Do you think things like the SIWO can function as a vehicle to preserve some of that? Or does it already?
What do you mean?
Some of the knowledge that might otherwise be lost, or might not be connected between different communities or something like that. It just seems like the SIWO could hold on to some of that maybe.
Yeah. There's an archive of all of the outlooks, and I think with some of the observation networks, you can go and look what has been submitted. Maybe not by whom, but you could definitely ask. What am I trying to say?
I got you.
There is the preservation of knowledge. I think I'm not sure how to put that. I don't know that it's necessarily a tool to archive and document knowledge as it is to share environmental conditions for decision making in the moment. But one thing that did come up with a lot of the literature on co-production with indigenous communities, or specifically Alaska Native communities, was the involvement of youth and education and passing on knowledge. So it is an indicator that I have in my framework, is thinking about how youth are involved in some of the co-production process or the decision-making processes, because that is an important value that I learned through my own literature review and some of the courses that I took in the last semester, fall. Does that answer your question?
Yeah, for sure. Thanks.
Cool. Yeah, thanks. Hi, Aurelia. Do you have a question?
It's nap time is what it is.
Okay.
All right, any final questions for any of our presenters today? If not, Nick and I would like to thank everyone who has helped us and presented over this academic year and who has attended. We really appreciate everyone's support. And with that, we do not have another salon to plug, so except for maybe in the fall. And I believe you'll have a new set of coordinators for that. So again, thank you everyone, and we hope you have a wonderful rest of the semester and a wonderful summer.
Thanks. Bye. Thanks, everybody.
Thank you. Very good.
Thank you.
Thank you.